Hi everyone, this is Kiranmai from H&S department. Today in this session, we are going to discuss about semiconductors current mechanisms like drift and diffusion currents. First of all, any motion of free carriers in semiconductors leads to current. This motion can be caused by electric field due to an externally applied voltage, since the carriers are charged particles. This transport mechanism is called as carrier drift. Drift means moving of particles due to applied voltage. Carriers also move from regions where the carrier density is high to the regions where the carrier density is low, which is called as gradients. Gradients means there is a change in concentration of carriers from one region to another region. If the carriers move from a higher concentration region to lower concentration region due to thermal energy and associated random motion of carriers, then the mechanism is called as carrier diffusion. In semiconductors, the total current is due to the sum of drift and diffusion currents, both due to the motion of carriers, uh, due to motion of carriers due to applied voltage, and the motion of carriers due to gradients of concentration of carriers. First of all, let us calculate the drift current caused by the application of an electric field E. Due to application of electric field E, the carriers in the semiconductor material will move with a velocity Vd called as drift velocity. So this drift velocity is proportional to the applied electric field. If the electric field is strength is increasing, drift velocity is increasing. If the applied field strength is decreasing, then drift velocity also decreases. So Vd is proportional to E. So when you remove the proportionality, you have to place one constant. Let us call that constant as mu, which is called as mobility. So Vd is equal to mu into E. Let us consider a semiconductor material which is having a area L, area A, and length L. Then its volume can be given as area into length, that is AL, and it is filled with a charge Q. Then charge Q can be given as volume into number of carriers into charge of electron, that is Q is equal to volume AL into number of carriers N into charge of electron E. Then the drift current through the conductor is given by current is defined as charge per unit time, that is I is equal to Q by T. So I is equal to Q by T. So to calculate Q value, we had already discussed the charge of the semiconductor material as volume into number of carriers into charge of the electron, that is AL into N into E, whereas T can be expressed in terms of velocity. So velocity is equal to distance by time. Then drift velocity is equal to length of the semiconductor by time. That is time is equal to length of the semiconductor by drift velocity. So in place of time, just replace it with L by Vd, rearranging the terms, drift current density. So, rearranging the terms, current is equal to A NEVD. So drift current density is defined as J is equal to I by A, where I is current per unit area. Current density is given by current per unit area, that is A into NEVD by A. Cancelling area, you are left with NEVD. In semiconductors, the current density is due to due to the mobility of both holes and electrons. Therefore, current density due to electrons is given by NEVD, that is equal to NE into, well, drift velocity can be given in terms of mobility as mu into E. So mu E E. And drift current density due to holes is given by NEVD, that is PEVD. Why we had replaced N with P? Because of the concentration of holes can be given as Pe into mu H into E. So J drift can be given as the summation of drift current density due to electrons and drift current density due to holes. Substituting those values, you'll get J drift is equal to E into N mu E plus P mu H into capital E, where E into N mu E plus P mu H is called conductivity of intrinsic semiconductor. So J drift current density is equal to conductivity of intrinsic semiconductor into applied field. Then coming to the diffusion current, as already we had discussed, diffusion current is due to the gradients of carrier concentration. That is, one area is having higher concentration, another area is having lower concentration of same carriers. Like in p-type, we can observe that there are majority carriers of electrons, but on n side, uh, on p side there are majority carriers of holes. In the same way, on the n side there will be a minority carriers of holes. Hence, when we p and n join together, so p side is having a higher concentration of holes, n side is having a lower concentration of holes. Similarly, n side is having higher concentration of electrons, whereas p side is having smaller concentration of electrons. When you join them together, there will be a concentration gradients. Hence, carriers will move from one side to another side, constructing current in the circuit. In the same way, consider the direction of current flow in the positive x direction, then the current density is directly proportional to concentration gradients according to Fick law. So current density is proportional to minus E into dN by dx. This negative sign indicates that current direction is opposite to the flow of electrons. So for electrons, we can write it as Jn is equal to dn into E dn by dx, and for the holes we can write Jp is equal to minus dp into E into dp by dx. Now net current diffusion density due to diffusion is given by J is equal to current density, diffusion current density due to electrons plus diffusion current density due to holes. Then summation will give you J diffusion is equal to dn into dn by dx minus dp into dp by dx into charge of electron. Hence, current density due to the drift and diffusion currents in a semiconductor is given by current density is the summation of both diffusion current density and drift current density. So, summation of J drift plus J diffusion, just substituting their expressions in the final one, this will give you the total current density in a semiconductor, which is due to both diffusion and drift currents in the semiconductor. Thank you.